Okay, so everything is working, seems. All right, so we're back to where we were last time. So I was describing there is the basic ingredients that we have for this formalism of well, I haven't yet described what these merge operations are, but I described what the syntactic objects are. So they're binary, non-planar of abstract, non-planarly embedded binary rooted trees with leaves decorated by your finite set of lexical items and syntactic features. Workspaces are just forests made of such binary rooted trees. And accessible terms are pieces of the structures that comprise the workspace, where you can extract some. So there are those subtrees that hang below one of the vertices. So the accessible term of a single syntactic object are those subtrees that hang below one of the vertices, including possibly those that are a single leaf decorated by the corresponding lexical item like features. And the accessible terms of the workspace also include the possibility of singling out an entire component of the workspace. So I was saying that the kind of, so I described last time the algebraic structure underlying the syntactic objects themselves, and said that they form magma with respect to this operation that constructs binary rooted trees. But I was saying the workspaces have a different kind of algebraic structure that's naturally associated to them, and they take it into account these two operations, putting together a workspace consisting of individual syntactic objects. So this basically this disjoint union operation, and extracting the accessible terms that one wants to use as material for calculation. So what I suggesting is that the correct kind of algebraic structure that accounts for this combination of operations is a Hopf algebra. And the idea this is that the Hopf algebra has a combination of an operation that assembles structure and an operation that decomposes structure, the product and the co-product. And the product operation would be the one that accounts for forming your workspace, and the co-product for accessing the accessible terms. And one point that I want to make, which I will actually come back to a little bit later in the class when I start talking about how syntax interfaces with semantics, is the fact that if we're trying to argue that this construction of this merge operation that I still have to define how it works, is the basic operation, the basic calculational mechanism, computational mechanism underlying the formation of structures in language. Then it has to serve a dual role, right? It has to function both as a structure builder because we produce language, but it also has to function as a parser because we receive language that we have to interpret. So we need a kind of the same basic formalism to account for both things at the same time. And so what I will argue later is that this same formalism that allows for the construction of as a structure builder will also function as a parser. And this is again the fact that this coproduct operation is able to access all the sub pieces of a structure, and part of the parsing is exactly finding consistency between those substructures, and so that will be the key. But I'll mention it for later use. Okay, so let me come to the Hopf algebra idea. So as I said, Hopf algebra accounts for this kind of composition decomposition operations. And so a product has two inputs and one output as assembling objects, and a coproduct has one input and two outputs. And typically, when you decompose something, in general, you don't have a unique way of decomposing a piece into its building blocks. You might have circumstances in which there is a unique decomposition, but in general, you might have a list of possible ways in which you can decompose something into two pieces. and which are the two outputs of the two output channels of your coproduct. And so in general, you want to have an output which is a list of possibilities. And of course, the simplest thing is to write that as a sum over all the possibilities. And the product also, it's in principle could have more than one way in which you can assemble building blocks together, in which case you would also have like a sum of possibility in your product. It just happens that in the specific case we're talking about, the product will have a unique way of assembling pieces, but in general, this is not the case. And part of I'll give the axiomatic formulation of what a Hopf algebra is in a moment, but I just want to explain why you formulate it that way before coming to the details. And one important aspect is that these two operations of assembling and disassembling should be compatible with each other. And as I already warned last time, this doesn't mean that they have to be inverse operations of each other. They have to have a specific compatibility that I'll formulate a little bit later, and it is formulated in such a way that it allows for a little more room for maneuvering than just saying that these two operations have to be inverses of each other. Because it's clear that what we are trying to get, right, requires something a little bit more subtle than just saying that they're inverse operations, because one of them is just will end up being just putting your a bunch of your syntactic objects together, but another one has this more sophisticated structure in the sense that you want to be able to reach inside a syntactic object for a substructure, not just taking out one component at a time. Right? So there will be exactly one of the cases where they're not inverse operations of each other.
Component, you mean literally connected components?
Yeah, so you can choose to act on an entire connected component of the workspace, but your decomposition. Well, so I'll say that more precisely in a moment. But of course, one thing you could do is just to model your coproduct exactly on the product, and say if your product puts together your objects in the workspace, your coproduct just separates them out. And that would also work, but the point is that the compatibility, the way it's formulated, allows you also for slightly more sophisticated operations that you can do that are not just these inverse operations. Okay. So in a sense, this is your picture, right? So a priori you have some building blocks, you have a product that gives you all the possible ways of assembling together, and you have also a co-product that takes an already assembled structure and breaks it into two parts in all possible ways. Of course, this example is deceiving exactly for the reason that I said, that in this case, these are exactly the two inverse operations of assembling and disassembling the same pieces. But in general, there's room for more. Okay, so let's get down to what exactly this means, right? So what a Hopf algebra is a vector space over some field. So for us, this doesn't really matter, right? What field you want to use? Let's just say the rational numbers for simplicity. In fact, you could also just formulate a version where instead of algebras, you talk about rings, and so you work with Z modules rather than vector spaces. But just for simplicity, say vector space over Q anyway, over some field. And then you have these different elements of the structure. There's a multiplication operation, and there's a unit for multiplication. There's a co-product, there's a co-multiplication, and there's a co-unit for the co-multiplication. And then there's an antipode that it interrelates these two structures. And this has certain formal algebraic properties. The multiplication is assumed to be associative, although you will find some special cases where people look also at cases with non-associative cases, but in general, it is assumed to be associative. And similarly, the co-multiplication is assumed to be co-associative. Because the associativity and the co-associativity, what they really mean is that iterations of these operations work well, right? They tell you that when you iterate either multiplication or co-multiplication, you don't have to worry about bracketing. So they are actually very, very well behaved. Those operations very well behaved under iteration. And and you have each of them has a corresponding neutral element. So a unit for multiplication and a co-unit for co-multiplication. I'll say in a moment what the exact properties of these are. And you also want to know that these two operations are compatible with the other structures. So co-multiplication and co-unit should be morphism of algebras. So it should be morphism with respect to multiplication, and multiplication and unit should be morphism with respect to co-multiplication. Okay? And the existence of this antipode map is so there are two constraints. One is a compatibility of multiplication and co-multiplication that is, that I'll state in a moment, is kind of this thing that generalizes the possibility that they're inverse of each other. And then there's another constraint that relates them, which is which is through the antipode. And this additional constraint, in principle, the antipode is a fairly strong constraint, additional constraint. But there's a specific class of Hopf algebras for which that comes for free. So the bi-algebra structure given by multiplication and co-multiplication is completely enough to also determine the antipode. And this one will be one of those. There's a particular class of Hopf algebra I will say more about in a moment, which are called combinatorial Hopf algebras. And they typically deal with composition and decomposition of combinatorial objects, which always have this property that the antipode is sort of given for free. You don't have to worry about checking that extra compatibility. So all of these properties, as usual, they are best described in terms of certain commutativity of certain diagrams. So when you say that, roughly speaking, when you say that you have a good pair of composition decomposition operations, you mean a compatibility in this sense, so that they form this kind of structure together. So just to know what these properties mean, the associativity, is just the fact that the multiplication is well behaved under iteration. So if you apply multiplication twice by multiplying one pair first and then the other pair, or the other pair first and then multiplying again, this diagram is commutative, means you get the same thing. So that's the usual associativity of multiplication. And the unit is the unit for multiplication. So when you multiply, you get back the same element, where you're using this usual isomorphism of the tensor product of the vector space with the underlying field with itself. And the co-multiplication and the co-associativity and co-unit, well, they are exactly the same diagram flipped, right? You're just reverting all the arrows. So a point of this observation is simply that there is this basic symmetry between the algebra and co-algebra structure of a Hopf algebra. And so in particular, this will mean that whenever you have a Hopf algebra, you also have a dual Hopf algebra, which is just the one where you reverse all the errors. And so the multiplication becomes the co-multiplication of the dual Hopf algebra. So it's based on the dual vector space, so functionals on your original vector space, linear functionals. But all the arrows get reversed, and so multiplication become co-multiplication and co-multiplication become multiplication. And so everything is just phrased in such a way that all the properties are completely symmetric with respect to flipping the arrows. And of course, you write the same conditions in terms of equations on the compositions or as commutativity of diagrams. So these are the two basic structures, algebra and co-algebra. And the next thing is that you have, as I said, one first condition of compatibility between the multiplication and the co-multiplication, which is given by this. So essentially, you want to say that if you flip the order of multiplication and co-multiplication, you get the same thing. But I mean, one has to be careful about what this. So they're not saying that they are inverse operation. You don't get the identity. You're just saying that if you flip the order of multiplication and co-multiplication, you get the same thing. But flipping the order means you have to do it in the right way, because of course, if you apply multiplication first, you go from 2 inputs and 1 output, and then back to 2 inputs. But now, if you want to go the other path and apply co-multiplication first, you first go to 2 pairs of 2 inputs, right? And then multiplying back. But there's one point here of what happens in the middle. So typically, when you look at the co-product, what goes into the coproduct have two outputs, right? So it's like a left channel and a right channel of the coproduct output. And usually what goes into one of them is of a different nature to what goes in the other one. So when you use algebras to describe combinatorial structures, the typical pattern is that what goes in one of the two channels of the coproduct is a sub-object, and what goes into the other channel is a quotient object. So they're kind of different roles. So if you want to, first disassemble and then reassemble together, you have to combine likes with likes, right? So you have to, at some point, to do a flip here in the middle so that the two left channels go together, the two right channels go together, and then you multiply. Okay, so the right compatibility has to have this flip in the middle, because otherwise you're mixing things of a different nature that are in the two outputs of the coproduct. So this is the basic compatibility that one requires between product and coproduct. And you might wonder what is it that happens if I, instead of doing product first and coproduct later, which gives this compatibility, which I want to have this compatibility. What happens if I do coproduct first and product later? Okay, I'll come to that, because that is an operation that have a very interesting structure in its own, and it has actually to do with one of these properties that I mentioned last time. This desired property that I mentioned last time of the linguistic model, which is that this merge operation should be Markovian, should be a kind of Markov process on the space of workspaces, and that will actually depend on this other operation. But that doesn't enter the axioms of the Hopf. There's no constraint on the reverse operation. The constraints of the compatibility constraints is phrased in this way. Okay, and then there is this fact that unit and co-unit, the way unit and co-unit behave respectively with respect to the other operation, co-unit with respect to product and unit with respect to co-product. So these are the compatibility between the algebra and the co-algebra structure. They are just ensures that you cannot choose them in completely arbitrary, independent way. And as I said, the antipode in principle gives you an additional constraint, which now is a constraint that assembles together in a single, if you write it out as an equation, assembles together in a single equation all the operations that you have in the Hopf algebra, because it relates coproduct, product, unit, and co-unit at the same time. Okay, so it's like the strongest constraint that you have on the Hopf algebra structure. If you don't have an antipode, then you just have a bi-algebra rather than a Hopf algebra. And so there's some additional property. As I said, I mean, usually the coproduct is a strong additional constraint on top of being a bi-algebra, but this is not always the case. So there's a special class of algebras that have the property of being graded connected. So graded means that as a vector space, it is graded. It has pieces of increasing degrees, labeled by the positive integers. And connected means that in degree zero, the degree zero part is one dimensional. So it only has a copy of the field in degree zero. But if you want, there's only one generator that is of degree zero. All the other generators are of some positive degree. And the product and coproduct have to be compatible with this grading. So the product is the product of graded algebras. So it takes something of degree K and degree L and gives you something of degree K plus L. So degrees add with respect to multiplication. And the coproduct is compatible with degrees in the sense that you split the degree in all the possible ways on the two sides of the coproduct. So you get all the possible decomposition of L into the sum of two integers, and your output is in one of those pieces or in several of those pieces, depending on the sum that you get. And so if you are in a case like this, so when your Hopf algebra has this structure, then you can actually determine the antipode for free. only using the bialgebra structure. And the reason is that there is an inductive formula for the antipode. And the reason for that is that the coproduct, in this case, because of this property, the coproduct is going to have something in top degree, which is got to be just of this primitive form, because then it has to be of the same degree of x. So x can be only x itself, either in the left or in the right channel. Just like you're decomposing it, is the trivial decomposition in which you either extract all of it and you're left with nothing, or you extract nothing and you're left with everything. But then all the parts that have two decompositions into smaller pieces, they only have pieces that are of strictly lower degree. Well, the degrees add up to the same degree, but the two parts are of strictly lower degrees. And so this means that you can write an inductive formula, because these things are of strictly lower degree. So you start in degree 0 just by so the primitive part, this would be I'll explain this in a moment, but this would really be just like the addition, the additive group. I'll say in a moment why. And so the antipode would just be the inverse, the additive inverse. And then you kind of correct for the fact that you have all these other terms by inductively correcting the antipode with the way it was on the lower degree terms. So if you use this formula, then one can verify that this property, this compatibility property that the antipode is supposed to satisfy actually holds, and so it's a well-defined antipode. And so you basically, whenever you are in this situation and you verify that your Hopf algebra is greater connected, you don't have to worry about the antipode. It comes with the rest of the structure, so you don't have to worry about it being there or not.
Could you show why that's actually correcting? Because I don't see for the second term how it's correcting. The first term is an additive inverse, but the second term seems a bit less.
Yeah, that's right. So I mean, you sort of have when you go back to this property, right? So you wanna verify that if I co-multiply first and then apply the antipode of one of the two channels and then multiply back. So this is co-unit composed with units. So co-unit in the case of these graded connected Hopf algebras is projecting out everything that's of degree greater than 0. So it's just projecting on the degree 0 part. And the unit is just the degree 0 inclusion of the degree 0 part. Okay, so this is basically the identity on the degree 0 part and 0 everywhere else. So you're saying that if you co-multiply, then apply the antipode and then multiply again, then you get back just a unit, just one in the degree 0 part. So it's so this is really saying that S is like an inversion it is like an inverse operation and in fact this is not just an analogy. It literally is an inverse operation in the sense that Hopf algebras are, in a sense that I will say more precisely in a moment, Hopf algebras really are like functions on groups. And so the antipode corresponds to the inverse of the group at the level of the functions on the group. But so the thing is that if you look at this equation, you can also do it degree by degree. So in degree 0, it's verified automatically because you only have the units and this all acts trivially, you get, and then in higher degrees, you verify it inductively using this formula for the antipode. And that becomes an inductive argument that the identity holds, so that this is a well-defined argument. Okay, so this is the basic. So as I said, these operations, product, coproduct, and antipodes, and unit and co-unit, they really sort of sound group-like, right? So sound and in fact, it's commutative Hopf algebras are really functions on groups in a very specific way. I mean, more correctly, one should say that they are dual to affine group schemes. So this sounds fancy, but it's actually a very simple idea. So if you just have a commutative algebra over a field, say your A is a commutative algebra over some field. Then this commutative algebra defines a functor from other commutative algebras to sets. How does that work? Well, I can take the homomorphism between commutative algebras. So I choose another target algebra, and I look at all the morphism of commutative algebras between A and that target algebra. This is a set, okay? So I have something that takes a commutative algebra. I'm given A as something that chooses another R and gives me a set, which is the set of morphism of this. And so the way one says it in algebra geometric language is that this algebra A is dual to a geometric object, which is an affine scheme X, of which A is like the ring of functions, the algebra of functions on that affine scheme. And this set that I compute in this way is the set of R points of that scheme. So it's in the sense this is just saying that if you have for example, let's take R to be the field K itself, right? So if R is the field K itself, I'm looking at algebra homomorphism from A to the field. But if A is the ring of functions of a space, this would be like points in a space. I'm taking a function and I'm evaluating it at a point. And this gives me an element in the field because my functions are valued in K. So when I evaluate them at a point, I get a point in K. And this is a morphism of algebras with respect to the pointwise multiplication of functions. So it's a way of saying what a point is. It's a kind of an algebraic way of saying what a point is. And if my target is K, this would be the K points of my space. But doesn't have to be K, it just has to be some commutative algebra. And so I have a notion of what the R points of my space are. And so that's the way in algebraic geometry, whenever you have a variety or a scheme that you find over a field, you can look at its points over not necessarily the same field, but some other field that's an extension of that, or some algebra for the same field. Okay, so this is just a set of homomorphisms. And A is just an algebra, commutative algebra. But now let's suppose that A is not just a commutative algebra, but it actually has a co-algebra structure. So it has also a co-multiplication. And it has also an antipode, so it's actually a Hopf algebra. But then this set of so I still do the same thing. I take exactly the morphism of commutative algebra. So these morphisms don't know anything about the fact that A has a coproduct. They just know that it's an algebra. But on this set now I have some new operations, because since I have a coproduct, I can take two of these morphisms from A to R, and I can evaluate the first one on the left channel of the output of the coproduct, and the second one on the right channel of the output of the coproduct. And this gives me a product between these two. I can define the product of two of these functionals by this pairing with the coproduct. And also because I have an antipode, I can define an inverse of one of these by composing with the antipode. And this identity that the antipode satisfies with product and coproduct is exactly saying that this is the inverse with respect to this product. So in the same way, I get a unit for this product from the co-unit for the coproduct. So now this X that is a priori just a set, now it's in fact a group. So it's this thing is called an affine group scheme, because again, it's whenever I choose R, I get a group, which depends on R. So it's like a family, it's a functorial family of groups, that depend on R. So commutative algebras are affine group schemes to this duality between functions and their underlying spaces. So that's why the axiom of Hopf algebra look very group-like, because you're just seeing a group from that's kind of dual perspective, right? Okay, so that's another way of thinking of what is. All right. Well, so here's some simple examples, right, of what I just said. So the simplest example in which you see a Hopf algebra is dual to a group, you just take the algebra of polynomials in one variable. So it's as an algebra, its dual scheme would just be like the affine line. The variable is just the functions. It's a functions on the line. Polynomials are algebraic functions on a line. And now we make it into a Hopf algebra. So we take the coproduct that is just of this primitive form, and the antipode would just be the additive inverse in this case, minus x. Okay, so what happens if I apply the recipe that I described? What is the product now between morphism or from this algebra to some other algebra? Well, it's pairing with the coproduct. So I apply phi1 to the first term to the left side of the coproduct, and I apply phi2 to the right side. So I just get phi1 of t plus phi2 of t. So it's the additive group because the group operation is addition. Okay. And same thing, other simple example, the multiplicative group is now, well, the next simplest example of value is, the algebra of Laurent polynomial, where now t is assumed to be invertible, not just, so it's polynomials in t and t inverse. And now I make a coproduct that just like this. So when a coproduct of this form is usually in the Hopf algebra terminology is called primitive. And an element that has a coproduct like this in the Hopf algebra terminology is called group-like, for whatever historical reason. That's all. And so if you pick this as the coproduct, then when you multiply these two together, then you actually get exactly multiplication. So this gives you the multiplicative group as a group scheme.
So can you remind the morphisms and the unit is going to what?
Well, so a priori it's just going to some other K algebra. Right. So this would give you, if I fix to which K algebra they're going, say R, then this would be the R points of the additive group, and this would be the R points of the multiplicative group. Like GA of R or GM of R. And that tells you what was the target of this morphism. But the point is that the form of the operation is the same, regardless of what the target is.
Why do you need T inverse in the multiplicative?
Yeah, so that's sorry, I didn't write out what the antipode does in this case, but the point is that here the antipode sends t to minus t, and here the antipode sends t to t inverse. If you want it to be compatible with this product, this is coproduct. Yeah, that's why you need t inverse. Yes. And okay, so you can do other examples like this. Like for example, you can take a GLN, is also a group scheme, and then you take polynomial algebra on variables Tij, and the coproduct is dual to multiplication of matrices. So the coproduct of Tij is like T, the sum of Tik tensor Tkj. And then you see that when you do this, you get matrix multiplication. And yes.
So if you have some variety over K and you look at the K kind of points, you have some group of advisors lying behind the structure, elliptic curves. Is that the same kind of group operation? The close points of the elliptic curve?
So the elliptic curve is not an affine scheme.
And not a fine, a group scheme in general.
Right, but so in a sense the picture that I'm doing here is just a fun because you have like a single chart. But I mean this so yeah, if you have modulo that if you have a product structure.
Yeah, so my question is, usually in that context, we talk about k-valued points because the variety or the curve is over k, but can I also talk about r-valued points in general? Or,
Yeah, no, that's right. So you can, I mean, the point is that so if, for example, if I have an affine scheme that's defined over Q, right? That means just that the structural relations that define are, like, for example, if you take GLM, right? The only relation that I need to put is that the determinant is invertible, and that is a relation that's defined over Q. So I can say this is an affine group scheme that's defined over Q. But then doesn't mean that I can take it just its Q point. I can take its Q bar points. I can take its C points. So I can have GLN of C, GLN of R. You know,
there's some descent going on.
the things that, you know, each of these, if I have another field that's a field extension of the one over which the scheme is defined, then it's also an algebra over it's also commutative algebra over the field of definition. So I can take that as the target and looking at morphism of algebras like from Q to C, and then that would be, yeah. Okay. Okay. Fine so far. All right. Okay, so as I said, in particular, there's this particular class of Hopf algebras that are, you know, called combinatorial Hopf algebra. So I mean, historically speaking, you know, Hopf algebra first came into the scene in mathematics exactly as functions on groups, as kind of dual objects to groups. And a lot of examples of algebras, you know, come out of that perspective. For example, quantum groups are like a very famous class of algebras that, you know, are you know, obtained by taking, you know, the algebra that's dual to certain Lie groups and then deforming those into other algebras that are no longer themselves dual to Lie groups, but they kind of look like, you know, the symmetries of certain kind of quantum spaces. And so they look like a useful way of describing symmetries in quantum physics, you know, that are modeled on symmetries of classical physics as deformations. And so that's like one setting, you know, in which Hopf algebra is being used a lot in mathematics and physics. But there's this other perspective that was actually coming mostly from you know, Giancarlo Rota's approach to combinatorics, which is to actually try to, you know, think that Hopf algebras are a very natural structure underlying combinatorial objects. And so that so these type of Hopf algebras are based on the idea that the vector spaces that you consider are spanned by some basic classes of combinatorial objects. So like trees or graphs or matroids or any various classes of combinatorial object partitions, and the grading. So these are usually these graded connected of algebras, and connected means that there's a unique most basic structure that has like no extension, and the grading is some kind of size of your combinatorial objects. Like it could be number of edges or of vertices for a graph, or some kind of rank for some integer measure of size of your combinatorial objects. And so this as a vector space, it's spanned by combinatorial objects and graded by their size. And the product and coproducts describe ways of assembling like larger objects on the basis of smaller ones, or decomposing larger objects in terms of simpler ones. And so for that reason, it's also helpful in trying to understand what type of structures certain classes of combinatorial objects have, and enumeration problems of representation into like mapping the corresponding algebras to other algebraic structures, and so on. That's there's this whole development of what point of view on combinatorics based on Hopf algebras. And so, of course, the setting that we have is very naturally suitable for this perspective because we are looking at combinatorial structures that are coming from trees and forests. Okay, so let's get back to our specific setting. So as a vector space, we can take the span of the forest of non-planar binary rooted trees with leaves decorated by our set of lexical items, syntactic features. The grading there's a natural grading in this setting, which is by the number of leaves, because the number of leaves is the length of the sentence in terms of its basic word components or lexical components. So you can have a grading by how long strings of sentences you're forming.
Not by how complex they are, how many internal nodes there are.
Yeah, the thing is that these are binary rooted trees, and they are so if you have k leaves, you have k minus one internal non-leaf vertices. So the size there's essentially a unique way of defining the size, which is natural in this case. So that's also helpful in the sense that you don't have to. And so you can formally include a kind of empty forest. That's helpful because when you, as I said, when you want to do this coproduct, you want to include the possibility where you either you don't decompose, right? You just take all or nothing. So you need a nothing to describe this all or nothing choice. So you also add a formal object that's your empty forest. And now the product is just this disjoint union operation on takes two trees, puts them together as a forest, or take two forests and puts them together as a larger forest. And of course, the empty forest is the unit for the disjoint union for product operation. And the product is compatible with grading because the number of leaves adds over disjoint union. And now we have to decide what to do with the co-product, right? So we have decided what the product should be, and we need a co-product operation that satisfies this compatibility. And as I said, I don't have to worry about the other compatibility that comes from the antipode because of this graded connected property that will come for free, but this one I have to worry about. So here you have like two different choices, right? The simplest one is you decompose your workspace into its constituent syntactic objects, the way you put it together. And the other one is where you actually extract the accessible terms. So if you do the simplest thing, right, in which your decomposition is actually the inverse to your composition operation, then this would really be like requiring that each tree component by itself is indecomposable. It's no further, you don't access any further structure. You just take it as a whole, or take it or leave it. So you can make a coproduct by requiring that all the trees are primitive elements. So now this will determine it on everything because we know that the coproduct has to be a algebra homomorphism, and the product is a co-algebra homomorphism, right? So we know that on a forest, it has to be the product of what the coproduct is on each of the components. Yes.
So how do you define the decomposition of the index set into I prime and I prime?
Okay, so I'm just following this, right? So the only thing I prescribed is that trees are primitive elements. And then I'm saying that this determines what this should be, because then it's the product of these, right? But suppose you have two of them, like you have your F is TA disjoint union TB, right? T1, T2. Then you have T1 tensor 1 plus 1 tensor T1, and product with T2 tensor 1 plus 1 tensor T2. And now I'm taking the product of these two, right? So I have T1 product T2 tensor 1, T1 product T2, T2 product T1, and 1 product T1 T2. So what I'm doing so the co-product of F is just all the partitions of your disjoint union into two parts.
Oh, so the product, so the sum is over all parts, like all parts.
That's right. So these are like all. So if F is the union of in some indexing set of your trees, then you partition this indexing set in all possible ways. And one part of it goes into one side and the other part goes into the other side. So if I,
Shouldn't you write the other way around in the condition? Just to be sure.
yeah, this is symmetric, right? So this is actually co-commutative.
No, I was talking about the indexing of the
Yeah, the
summation. It
sum.
should be the other way around, right? I
Uh,
dash union I double dash is equal to I.
I think it's equivalent, but that's
Yeah.
why I ended up getting confused.
No, because that presumes that your conditional variable is I, but that's what you already know. That's not what you don't know. That's what.
Okay, no, I think it's sort of, no, it's sort of convenient to say that, yeah, you partition, right? Your partition in all possible ways, your disjoint union into two parts.
Mhm.
And one of them is, yeah, the left part and the other, the right part of the part. You sum over all these partitions of your forest into two forests. And so this has the property, the additional property that is not just co-associative, but it's also co-commutative, because now this is symmetric with respect to switching the two parts of the co-product. Over once you take each term is not symmetric, but once you take the whole sum, it is symmetric with respect to this. And so, I mean, the Hopf algebra being co-commutative means that its dual affine group scheme is commutative. And in fact, the dual affine group scheme is just every variable behaves like the additive group, right? So this is like a huge additive group on all of these variables, on infinitely many variables, one for each tree. It's just this infinite product of copies of the additive group. So it's an infinite dimensional affine space with this additive structure. Okay, so as I will discuss in a moment, if one would if I decide to take this as my co-product, this would account for one of the linguistic operation that I want to have, which is called external merge, which is the one that forms structure, that assembles structure, but I mean, to make this precise, I still have to tell you well this is defined, but no, I just want to mention it here. But it will not be enough to account for these other kind of operations that allow you to do movement on sentences that are already formed. So the answer to this is that, okay, this relation between product and co-product is too simple. You want something where the co-product is allowed to be a bit more complicated than the product. This is just the product itself, right? No, nothing more, nothing less. But now let's make a co-product that is more interesting than the product.
Sorry, before you do that, in the previous case, you were saying that it's indecomposable based on any arbitrary co-product, right? If any co-product has an input that's like in that sense indecomposable, like you're just getting two copies in two different channels. But like, is that useful at the end of the day for anything outside of this external attaching things to the external?
Yeah, no, as I said, if you have an algebra like this, like where all your variables are primitive with respect to the co-product, then it just copies of the additive group. So it's just like a big affine space. I mean, okay, affine space is a useful thing, but but it's just that it doesn't contain a whole lot of structure. So yeah.
But this presumably is used in other places outside of this context, right?
Yeah, no, that's right. I mean, as I said, it is, what this basically describes, and if these are just variables, right? Let's forget that they are trees or anything. Let's just imagine that these are just abstract variables. What I'm describing is just an an affine space on this number of variables. So wherever you need an affine space, you can describe it like this. Okay. Yeah. In this context, it kind of has an interpretation, which I'll come back to, but
I guess I was asking if you took inspiration from that or it was the way around. It's something that you can find interesting in this context and
yeah, so that I will come back to, yeah, because as I said, there is this, because I haven't yet defined what this operation is going to be, but as I said, has something to do with what happens if you make a composition of coproduct followed by product. And that will be, can actually apply in other setting. Yeah, I'll say how that looks like in other settings as well. Okay, but so let's try to make the coproduct a little more interesting. So we cannot do, again, we just have to define what the coproduct is on the trees, because on the forest is just a product of those. So we have to define it for trees. So we do the same thing up to here. So there's going to be a primitive part in the sense that you're allowed to just take the entire tree or take nothing. Right? So that is still an option. But now you have the option of doing other things. And what are these other things? So I have one of these, binary, the trees, and again, it's drawn in the plane, but it's like non-planar, it's hanging up there. And I cut it in some way. So what kind of cuts I want to use are these things that are called admissible cuts. And it just means the following thing, that I should never cut twice on the same path from the root to one of the leaves. So for example, I cannot cut here and here. But this is okay because each of the cuts is only on one path from the root to one of the leaves. And so what's good about this cut, that if I do this, what falls off is a collection of admissible terms in the sense that I defined before. So I get some vertex, and everything in the tree that's hanging below that vertex stays together. So it's and then I have some part that is left. Okay. So I'm gonna define my coproduct by making all of these possible choices of admissible cuts. And in the left channel of the output of the coproduct, I put whatever falls off. So what falls off in general is a forest, not a tree, unless I have an elementary cut that only cuts one edge. So that will be like the first term here would have the cuts that only cut one of the edges, but then there would be all the ones that also can also cut more stuff. Okay. So but the left-hand side in general is a forest. The right-hand side, I have to put what is left. And so, and as I'll say in a moment, there's slightly different choices about how you define what is left. But it's certainly clear that whatever your fine print, of how you define what is left is something connected. So it has to be a tree of some kind. So here's an example of the fact that I mentioned, that what goes in one channel of the coproduct is of a different nature from what goes in the other channel. In the left channel, you're going to see forest. In the right channel, you're always going to see trees. So this is no longer a co-commutative of algebra. It's commutative, it's co-associative, but it's no longer co-commutative because you cannot flip the two sides of the coproduct. They really are objects of a different nature. And so it means that the dual group scheme is a non-commutative group. It's a non-abelian group. It's no longer like the additive group that is an abelian group.
Question?
Yeah.
Did you define the quotient like this earlier, or is this the first time you're doing this?
Yeah, so I'm gonna come to how we want to define this quotient. So
it's not contracting the whole thing.
Yeah, so the thing is like, okay, you remove this part. Okay. Now there's a few things that you can do here, right? Because what you're seeing here, let's say that I'm cutting off, right? So I'm definitely removing this, but then three different options. I will discuss them more. But there's three different options. One is to say, I actually just shrink all of these things to a single vertex. So this root vertex here remains attached here, but it also goes into a copy that I'm extracting. Another thing I can do is to just remove these things and remove the edges that I'm cutting. And then I'm left with a tree that, however, is no longer fully binary, right? Because it has, for example, if I cut this edge, it has a non-branching vertex here. And it has another non-branching vertex here. So I have to allow for this kind of non-branching vertices as well in the part that I have left. Or there is an additional option, which is to say, well, I have this tree which has these non-branching vertices, but there's a unique maximal tree without the non-branching vertices that's defined by this, right? And I can take that. So there are three possible options. And the thing is that these three possible options are all useful in the sense that they actually take care of different things in the model, but they do have slightly different algebraic properties. So one has to kind of take care of all of them together and their interaction as a way to deal with it.
Sorry, one more question.
Yeah.
C is a set of cuts.
That's all. C is the set of cuts. So here you can think of this as being a sum over the set of cuts, or a sum over the vertices that are the roots of the things that you cut off.
I was wondering how the first option differs from the third option, like the first one where you can graph each subtree into like a single node.
Yeah, I'll show that more precisely in a moment. But the first option, these root vertices remain part of the remaining tree. In the third option, they don't.
Oh, I see.
So here's the example of what this decomposition now look like, right? So composition is uniquely defined as just this joint union. The decomposition has all these pieces. Here I wrote down the case where you take the actual remaining binary tree on the maximal binary tree determined by the one that has the non-branching. Okay, so this I've already mentioned, right? You have this. So just as notation, right? I'm going to write. I'm going to equivalently write. So this kind of algebras of rooted trees, of course, have already been looked at in the literature, especially in physics, where you do this chains of nested divergences in Feynman graphs. You describe them by this, basically the same algebra of rooted trees. And so I'm going to write this for the forest of a certain admissible cut, but I also write it equivalently as the corresponding collection of accessible terms. And I'm just going to use this notation when I want to indicate the corresponding remaining tree that has also these non-branching vertices included. Okay, so now what that means, if I want to keep these non-branching vertices, is that I just have to slightly enlarge the vector space that I'm working with, because now it's not just spanned by the full binary tree, but I also want to allow binary trees that can have some non-branching vertices somewhere. So in more generally, like I can. So of course I could in principle have a forest with arbitrary valences of vertices, and I could make a Hopf algebra with the same criterion, regardless of the valences of vertices. I mean, I can make a Hopf algebra of trees, of rooted trees of any arbitrariety by the same principle of the admissible cuts and the corresponding remaining terms. And And there, of course, everything would be in the same vector space because you allow any values for the trees regardless of and they're not supposed to all have the same vertices, they're supposed to all have the same values. But you can take the subspace of those forests where the valencies are bounded by a fixed n. And this would still be compatible with this coproduct because you at most lose some valencies of trees when you cut. You never gain higher parity. So this would all be sub algebras where both product and coproduct will respect that. And so in particular, you can look at those trees that are binary, but where the additional possibility of having non-branching vertices rather than branching, than binary branching. And so this coproduct, right, the one that uses the admissible cuts and just takes literally what is left when you remove the edges on cut, is a coproduct that's defined, from the vector space of full binary trees, and then when the thing that falls off is still a forest that's fully binary. It's what is left that can acquire now this. So the coproduct is actually going this way. So what does that mean?
Well, why did you have to take it as a forest? Can't you just say tree? Because the right channel is listed.
No, that's right. But for now, I mean, this side. No, of course, this side you're just gonna have trees, but this side you're gonna have forests. So I mean it's just convenient to take it. But you're right that this would actually end up into the subspace that generated by trees. So what is this, right? Because I mean now there's this slightly embarrassing situation that the two channels of the coproduct are not in the same vector space. All right. So this is okay in the sense that what you are describing is a slightly different algebraic structure, and namely, you can have a co-module. That's what this is describing. So let's look at exactly what is happening here. So the so coming back here, this left channel is exactly in the same place where you start. It's this one that is sort of ending up somewhere else. Okay? And the co-associativity condition actually works, up to this fact that you end up in this slightly larger vector space, but the actual identity of the co-associativity works. And so what the way to describe exactly what is happening here is this structure of co-module. So this is, of course, dual to what a module over an algebra is. So if you have a module over an algebra, it's a representation of the algebra. So it's a vector space on which the algebra acts. So, and the fact that the algebra acts means that the multiplication in the algebra has to be compatible with the action, right? If I take two elements in the algebra and I'm acting on an element in the module, so I have A, B, and V, which is like an element in my module. So I can act with A on V, and then I can act with B on AV. And this should be the same thing as first multiplying A and B in the algebra and then acting on V with the product, right? So this means that a condition that tells you that this is an action of the algebra is formally the same as the co-associativity property in the algebra, except that one of the arguments is in the module and not in the algebra, right? And so the co-module property is the same with all the arrows involved. So it means the following, that I have So the action of an algebra would be like a multiplication, right? Except that one of the two elements that you're multiplying is in the module and the other is in the algebra, right? So this looks like a co-multiplication, but one of the elements of what you get is in the module, right? In the action, you have an element in the algebra, an element in the module, and you get a new element in the module. Here you get an element in the module, and you get something in the module and something in the co-algebra. And the same property that I said before, right? That you can first multiply in the algebra and then act, or first act, and then act again, is which is formally the same as the associativity in the algebra, but with one of the argument in the module is this what you do here. So you write the same formal expression as the co-associativity property in the algebra, except that once it's the coproduct in the co-algebra, and once it is the co-action. And so this is exactly what we have in the case we're looking at here, because this is the co-module, and you are sorry, this is the co-module, and so this is the co-algebra, right? Because this one, whenever I fix whenever I allow my tree to have valencies less than or equal to n, that is a Hopf algebra effect. So this is the part that is the Hopf algebra, in particular the co-algebra, and this is the co-module over this co-algebra, as it really is a co-module over the Hopf. And so the module is this space of fully binary forest. And the co-action is just the co-product restricted to this. And the co-product in this larger of algebra, or less than or equal to, valence is less than or equal to. Right. Okay. So this is a slight twist in the story, right? It's that happens when you take this form of the what is left when you take out a bunch of admissible terms.
Are you going to use that, this co-product?
Yeah, so the things, as I said, I'm going to have to use everything because they mean different things. So because I'm going to have to use everything, I have to see like what are the relations between all these things and what kind of properties they satisfy. Okay, so this is one option, right, for how you define what is left, which is just to take this trees with non-branching vertices. And this is this thing, and I'll say in a moment what this means. So the role that this has in the linguistic model is that these non-branching vertices are keeping a trace of something that you have moved in your structure. And there is this other form, which is the one in which you contract the pieces that you are extracting. And then there is this one where you delete them and you take the largest binary tree that's determined by what is left. Okay, so I've described already what kind of property the first option has, and let me just describe what happens with the other one. But so here's the picture of how these three things differ, right? So let's say that I start with this tree, and now I want to extract this subtree, this alpha beta substructure. So I do the cut on this edge that just above this alpha beta cherry tree. So the contraction part is the one in which this whole thing becomes just the root vertex in what is left. And I attach a label to that, which I'll explain better, but it's a label that kind of remembers something about the structure that I moved. Of course, I want this something to be something that is available in my set of labels, because I don't want my set of labels to become infinitely large. So it means that basically what is the point here is that I will want to remember that although I have moved this substructure, I'm going to use it somewhere else. I want to remember that it was there and it was playing some kind of role in that syntactic object. And so, for example, I can keep track of what the syntactic feature associated to that substructure was, and keep that as my U label for that remaining vertex. And of course, the other thing is that I can instead cut this whole thing, and I'm left with this non-branching vertex. And I could say, okay, this is no longer a labeled leaf now, but so this is like keeping a little less information. So this remembers that something was removed, right? But you no longer keep track of what feature it had, like what role it had. It's just enough to keep in mind that something was moved from that. And the other thing is that, okay, now you can say what is the largest fully binary tree that's determined by this one. Well, you can contract this hedge here if you want to remove this non-branching vertex, and then this would be this other time. And here you have actually completely, so any trace of the thing that you have moved out has completely disappeared. And so I'll come back to say what I mean by this sentence at the bottom, but let me just say it quickly. So when I was doing this brief overview of the linguistic model last time, one thing I mentioned is that when you move structure, for example, to form, I don't know, for example, to pass from, in English, that happens when, for example, you pass to the passive form of a sentence, you take an element and you move it up front in the sentence. There are two things that happen. When you parse the sentence, when you interpret it, you sort of know that element, where that element belongs. So you know that it has been moved. So it's like you still know of the presence of a trace, what those linguists call the trace of the element that was moved. But at the same time, when you externalize language, that part is no longer visible. In the actual string of words, that part has completely disappeared. And so it appears only once where it has been moved. It doesn't appear where it came from. So this is like saying that when you are interpreting your structure, you are actually using one of these forms, but when you are externalizing it, you're using the other form. And this accounts for this fact that there are these two apparently different ways in which the thing that has been moved behaves. And indeed, there are different ways in which the thing that has been moved behaves, because when you try to define this coproduct, you do have these different options. And all of them are possible as choices. Okay, so this is in a sense what the linguistic interpretation for these three forms is. When you take this contraction part, this is the part that goes to the semantic interface for interpretation, and the part that is just entirely disappearing is the one that goes to the externalization, and the thing in between is the one that relates these two. That, remember how you go from one to the other, because you do have projection maps from between these three different levels.
Question?
Yeah.
So if you go back to the
Yeah.
previous thing, you said that you can label the contracted, what's left as one, root, sorry,
right.
embedded element. For that, you need some information from your lexical item set, right?
That's right. Yeah. So, for example, let's imagine that this alpha beta term was, I don't know, like a noun with an adjective, right? So, okay, well, I don't need to remember exactly what that noun and adjective where because I still have them. No, I'm moving them. I'm not, deleting them. So they're still available. But I need to remember that, for interpretation, I need to remember that in that place, there was a noun phrase. So I could just have my syntactic label, syntactic feature label that says, okay, that was a noun phrase. And then I know what, because it's still there. So I know which noun phrase it was, but I just need to know where it was coming from and which role it had in the place where it was.
So for this example, if you look at this one, in which you're also getting rid of two, but you're retaining one piece of information,
That's right.
it's just not at the base anymore. It's somewhere in the middle. So
Right, yeah, exactly. So if you want to say, this is just saying something was moved. So you're not labeling it by the corresponding, you're not here, it's an internal vertex, so it's no label, right? So you're not even labeling it with whatever syntactic feature it had. And you're just saying, okay, maybe this is sufficient information for, or once you know that something was moved from there, I mean, you can still parse what it was. Okay, so let's look at these other options. So let's say that I'm doing now the coproduct by contracting the things that I taken out. I just contract them to the corresponding root vertex, where I attach this kind of syntactic feature that was carried by my substructure. That I use just this symbol, because that's usually the way that in the linguistic paper you write it by kind of crossing out the part that was present there. And so this is this form of the coproduct. So here again there's some slight things one need to be slight details that one need to be careful about in terms of what the algebraic structure is, because of course now if you are grading by the number of leaves, then the counting does not add up, right? Because these root vertices remain also on the other side, and they are counted still as leaves, so they don't add up with the grading. But if you count by edges, then it does add up. Okay, so in this case, the appropriate counting of size is taken care of by edges rather than by leaves. And this of course has an issue, because once you're counting by number of edges instead of number of leaves, you're left with something that's no longer connected as a Hopf algebra, because you no longer have a single element of degree 0, because just the single element of degree 0 would be the tree with one, would be just a single vertex now, so 0 edges. But you have a lot of them because these are decorated. This would be just a leaf, a single leaf, and leaves are decorated by elements in your set of lexical items and syntactic features. So you have a lot of them that are not the same. Okay, this is
you have exactly as many elements in your set.
as many as your elements of your set of lexical item and syntactic features, which is potentially a very large number. But it doesn't matter. So it matters that it's more than one. But so this is not a big deal in the sense that, okay, it's a Hopf algebra now with this coproduct. It's a Hopf algebra that is graded but not connected. Well, the only thing that you lose if your Hopf algebra is graded but not connected is that when you try to define the antipode, there are certain elements on which it will not be defined by that inductive formula, which are exactly these elements of degree 0 these additional elements of degree 0. And okay, that's fine. So what you get something which is co-associative. No, everything is fine with that. But okay, it's a bialgebra, with this coproduct. And the only thing is that it's a Hopf algebra only on a certain quotient, which is the one where you quotient out by the ideal, where all of these things are identified with the trivial one. So basically, okay, it's the antipode would exist only on this degree 1 and up. subspace. That's okay. It's not such a, I mean, so if you use this, when you use this coproduct, okay, the only thing that you need to keep in mind is this fact. But effectively, this has no effect of consequence, because in all this construction, the antipode itself does not play an essential role. The coproduct does, and the product does, but the antipode itself does not play an essential role. So the fact that there will be a subspace here on which the antipode is not necessarily defined is like saying that, okay, so this situation would be when you think in terms of dual things, instead of being dual to a group, it would be dual to a semi-group. And a lot of elements in the semi-group will still be invertible, but there will be some elements in the semi-group which are the ones supported on this subspace of the degree 0 element that would not be invertible. Okay, so no, so I've already actually discussed this. In this when I make the coproduct in this way, as I said, in the term that remains, I have to give some labeling to these new leaves that are the root vertices of the accessible term that I'm extracting, and I put these leaves like this. And no, I've already mentioned this. The point is that I don't really want to think of this as being the entire structure that I remember, because otherwise now I would need a new label for each syntactic object, right? Because I could, I mean, if any syntactic object is going to occur as an accessible term in something larger, so it will be in some of these cuts. So there will be some root vertex that's decorated by a leaf like this. But so if I really want to, by this, I really want to remember the entire structure that I had there, I would necessarily end up with an infinite set of labels. Which, I mean, you could do, but no, there's strictly no reason for doing that. So that it's you don't want to be dealing with an infinite set of generators if you can deal with a finite set, right? So the point is that linguistically speaking, you don't really have to remember the entire structure because it's not disappeared. It's in the other channel of the coproduct, right? So you still have it. You just have to remember what role it was playing. And so you can keep your set of labels to be finite. You don't have to go to an infinite label. Although the terminology, the notation that one uses seems to suggest that this has become an infinite set of labels, but that it is not. It's just a syntactic feature that object carried that you remember. Okay. Okay, so I think I'll have to. Next time I'll explain the third form of this coproduct and what properties that has, and then I'll say how this enter in this merge operation that I haven't constructed yet.